Okay, so let me share. Okay, does everyone have R open? If not, I'll just give you some time so you can open it up. Okay, so I'm gonna, let's see. All right, can everyone see my screen?
Yeah.
Okay, so I'm gonna scroll up to where, okay. All right, so the first thing I'm gonna do is I'm gonna load my data set. This is just the NHANES data set that we created the first day that we looked at this exercise, so 2 weeks ago, where we merged those individual NHANES files into one, and then we did some recoding. And then I put here the different packages that you probably want to load for the functions that we're going to use. So I'm going to copy and paste that into the chat so that you can add that to your program as well. So we used all of these last week, but we'll load them again so that we can use them this or today. Okay. So how did everyone do looking at vigorous activity? Was that okay? It's basically the same code that we used for the moderate activity. If you look here, the only difference is obviously the observation numbers for the outliers are different. And then, you know, we chose to, interesting. Okay, there. We chose to remove them. And then what I wanted to do was go back and show you what it looks like if we were to run these tests but not remove them. So let me just, okay, right. So the last thing we did last week with the moderate activity, and so probably what you did as well with the vigorous activity, was to run the rank sum test. So it's this here for number 5, and that's the appropriate test, right? Because even after we removed our outliers, you know, our data was not normally distributed. And then we compared it. I went ahead and like ran a t-test to compare. So let me actually go back. Okay, so I apologize because we're gonna have to go back and I need to create these data sets just to show you. You don't have to run this. And then I'm going to put yes here. Okay. So vigorous, so NHANES underscore vigorous 1 is just the NHANES data with all of the missing, so individuals who are missing a value for vigorous activity, they're excluded. Let me just run up to that code and show that to you here. Okay, and then as well as individuals who originally had values of refused to answer the question or didn't know, so 7777 or 9999. If you remember, 2 weeks ago, we recoded those to NAs or missing. And so then this line is just removing all missing. So that ends up, that effectively removes those refused or don't know answers. Okay, so then here I'm just creating this new data set so that in case I do remove the outliers, I'm not, you know, removing them from my original complete data set where I don't where I have all non-missing values for vigorous activity. And then once I remove those outliers, this function, again, it recodes them to missing. So this line is just removing those missings again into a new data set. So NHANES vigorous 1 is my original data with the outliers in them. And then vigorous 5 is our data set without the outliers. Okay. So if you ran your rank sum tests on the vigorous activity with the outliers removed, you had a very small p-value, so it's less than 0.05. So then we reject the null hypothesis that there is no difference. So then we would then conclude that there is a difference in minutes of vigorous recreational activity by gender. Okay, and then I just put the code for t-test just for comparison, and it turns out the interpretation is the same. So our p-value is still less than 0.05, so we would still come to the same conclusion, whether we use the rank sum test or the t-test. And in this case, it just so happens that the rank sum test is more appropriate for our data. Okay, so, oh, okay. I'm sorry. So I didn't actually write code to run these tests on the data with the outliers still in them, but I did do that for general health. So hopefully you went ahead and tried general health on your own. If not, let's just do that together. We already looked at all of our assumptions, right, for moderate activity and for vigorous activity. So we don't need to do it all over again. And we already know that the rank sum test is more appropriate for both moderate activity and vigorous activity. So let's first look at moderate activity, and then I'm going to copy and paste this code for you. So we're still on question 3, but we're kind of on that second half of question 3. Okay, so if you remember, the mod 5 data is, the data set with the outliers removed. Okay, so let's run the rank sum test. Okay, oh, because I need to create these data sets. All right, let's go back. If you didn't close your, if you did not close R, you should still have these. If not, what I'm going to do is copy these into the chat so you can create the data sets that we're running to create this. Okay. So I'm creating the mod 1 data set. That's to create a data set that has all non-missing moderate activity, but that does include our outliers. I'm just going to go down and, okay. So I'm going to copy and paste this code into the chat as well. Let me run that. Okay, and then remember, we're just going to say yes in this case. So in your console area, once you run that outlier KD function, go ahead and put yes. Okay, and then now I'm going to create this mod 5 data set where I have all my outliers removed from the data. Okay, so now we should have the data sets that we need. You can kind of guess, right? Like right now, it's pretty straightforward, kind of straightforward because we are only looking really at one outcome variable and then one independent variable. But a lot of times what happens is we have, a data set with multiple, columns or independent variables that we're interested in. So let's say, for a particular analysis, we want to look at moderate activity as our outcome, but we're interested to see if, there's a difference by gender, if there's a difference by age, if there's a difference by maybe race, ethnicity, and we want to include all of those in our analysis, we would have to assess all of those individual variables and then and as well as our outcome variable. And if we have missings in those, then we need to decide whether to recode them as like, let's say a 9 and keep those people in our analysis or exclude them completely from the analysis. And you can see like maybe not so much in the case of these data, but for some data sets, and some variables that we might be interested in, we end up like losing a lot of people, which can actually become an issue. So it's really, this is why I say it's not controversial is not the right word. There's a lot of just debate, I think, about, what's the right method. And then again, that's where you really have to be familiar with your particular study and the context of your study. So, is it more appropriate to remove the individuals or is it more appropriate to leave them in? And that's, that's where like methodology comes in. And why statistics is maybe very straightforward. There's not a wrong answer. It's all math, based on in mathematics. But where methodology comes in is, okay, what's the appropriate statistic? What's the appropriate thing to do with our data? And that's where you can have, these sort of, discussions and disagreements with your colleagues sometimes. And oftentimes there might not be a right answer or a wrong answer. It's just kind of what's the best approach for your particular data and your particular study. Okay, so that was like long-winded. Okay, let's go back down. So this should run now because we now have our mod 5 data. Let me copy it and paste it again for you guys since it was like up above in the chat. Okay. So we ran our rank sum test. We're looking at whether there's a difference by general health status. And remember, that was a variable that we created. It had, I think, originally maybe 6 or 7 levels, and we just collapsed those into 2 levels where it's, I think it was like very good, good, fair was collapsed into 1 level, and then, poor, and I think 1 other level was collapsed into a separate. So now we have this binary or dichotomous variable. Okay, so we ran our rank sum test and we have a p-value of 0.0839. So based on that, we actually fail to reject the null hypothesis. And remember, the null hypothesis is almost some expression of equality. So, the difference or the moderate activity between individuals with poor health versus good health are the same. And we fail to reject that null hypothesis. So we would conclude then that there is no difference between these 2 groups for general health. When we run our t-test, we have the same result, which is great. It's consistent. We have, so even though the t-test is not really appropriate for these data, for the moderate activity data, we still do have the same interpretation. So our p-value is 0.131. So it's still greater than 0.05, and we still come to the same conclusion. Okay. And the nice thing with the t-test is it's giving you the mean minutes of moderate activity for the people with fair or poor general health. And it looks like it's 40 minutes. And then for individuals with good, very good, or excellent general health, it's 42 minutes. And then statistically, there's no difference between these 2 means. Okay, so now if you remember our _1 data sets were just the data sets where we remove the individuals with missing moderate activity, but we've left in the outliers in this case. So I just wanted to show you what that looks like. So let me copy and paste these for you so you can run those. Okay, and then I'm gonna go ahead and run both of them as well. Okay. So the nice thing is when we leave our outliers in for moderate health, we actually come to the same conclusion. So the p-value is 0.07. It's still greater than 0.05. So we would still come to the same conclusion that there's no difference in moderate activity between these 2 groups for general health. So if I were to look at this results, most likely what I would do, I probably still would have removed that individual with like 600 minutes, just because it's so extreme, and it's you can kind of think that person probably meant 60 minutes, but 600 was reported. And so I might remove that 1 person, which is a very small percentage of my overall sample. But I probably would decide, and this is just me personally, would have decided to leave everybody else in, because those individuals might have other variables that I'm interested in. So maybe I'm also interested in looking at, gender or, sedentary activity in those individuals. And if I were to move all 17% of individuals who were considered outliers with the, if you know, for the moderate activity variable, that's a pretty big loss of data. And those are individuals now where I'm no longer able to include them in any other analysis that includes moderate activity and some other variable that I might be interested in. So for me personally, my approach, because the interpretation is the same, whether I leave them in or remove them, I probably would have kept them all in, except for that one extreme 600-minute person. When we run the t-test, it's actually very close to 0.05. It's still less than 0.05. Most researchers, if they did get a p-value like that, they, you know, like, of course, you know, maybe you've heard of like publication bias, like papers or studies that have statistically significant results are more likely to be published. And of course, researchers are excited when they can reject the null hypothesis, because it suggests then that their research hypothesis is correct. And typically our research hypothesis, right, it matches up with the alternative hypothesis. So we want to reject the null hypothesis. We want to see a difference in groups. It's not as like exciting if it's like, oh, there's no difference in groups. Typically, there are definitely instances where that's not true, right? I know like last week we talked about race differences. I don't know if you've had a chance to look at the poster that I posted as an example, you know, but that, like, we actually found no differences in race for, you know, HPV vaccination among service members. And that was actually exciting for us because we do see differences in the general population. And we don't see that in a setting where everybody has health insurance. So in that case, you know, it was exciting not to see differences. But in most cases, by and large, researchers will want to reject the null hypothesis. So they would take this p-value, and even though it's very close to 0.05, they, you know, still say, oh, we had a significant result. So in this particular case, our t-test result doesn't match with the rank sum test. And that's okay. We know that the rank sum test is the more appropriate test. But it also highlights a very important point where selecting the appropriate test for our data is important. So it maybe wasn't so important up here where we had removed the outliers and we had the same results. So we would have interpreted it the same way, interpreted our results the same way. But with the outliers kept in, and it does include that 600, you know, minutes person. I didn't exclude them from this particular analysis. We do see that our interpretation would differ depending on which statistical test we select. So again, this is a good example of why selecting the appropriate statistical test is important. Okay, and then what I did was I just ran this for vigorous activity. So let me go back, and I know I said that, oh, don't worry, just watch me, you don't have to run this, which was, it turns out it's not true, so I'm sorry. Let me just copy and paste that so you can create the NHANES Vigorous 1 data set. And then I'll go ahead and copy and paste this code for you so you can run it. Okay. And then, all right, and then you would, once you run that outlier KD program, and it asks you whether or not you want to include or, I'm sorry, remove your outliers, go ahead and say yes. And then I will copy and paste that data. So then you should now have NHANES, the Vigorous 5 data. And you can see here, right, like if you look in my upper right corner here, we started out with 5,600 individuals, and now when we remove the outliers and we remove people, oh yeah, I will post this program that I'm running right now. I will post that to Cougar Courses. You guys will have that so you can like finish out this exercise. So great, you can see that you started out with 5,600 individuals, and when we start removing people who don't have data, so like even here, when we removed individuals who did not have, you know, a non-missing vigorous activity value, it goes down to like 1,300 individuals. You know, so we've really like kind of whittled down on our data set, which that in and of itself is kind of an issue too. But let's just move on anyway. So we have NHANES Vigorous 5. So now we can run our rank sum test, which is the appropriate test on the data that has the outliers removed, and then we'll just run the t-test for comparison. So I'm going to copy and paste this. And again, we're looking at vigorous activity by general health. Okay, so I'm going to run these as well. So in the case of vigorous health, we have a p-value of 0.366, so it's greater than 0.05. So we fail to reject the null hypothesis, and we come to the conclusion that there's no difference in minutes of vigorous activity, recreational activity by general health status. And then if you look at our t-test result, the p-value is 0.2584. So again, it's greater than 0.05. So in this particular case, we would come to the same conclusion, whether we use the rank sum test or the t-test. Okay. And then now I'm going to copy and paste this for you to run. Now I'm going to run those. Okay. So if I run the analysis with the outliers kept in, I come to the same conclusion actually, where the p-value here is 0.2039. It's greater than 0.05. So I would come to the conclusion that I failed to reject the null hypothesis, that there's no difference. So I conclude that there's no difference in vigorous recreational activity by general health status. And then as it turns out, the t-test comes up with the same result. Okay, and then this is a note for myself to discuss removal of outliers, which I think we did a lot of. There's just one other point that I want to make. So remember up here when we ran moderate activity and looked at whether there was a difference by general health status, and for the rank sum test, we failed to reject the null hypothesis. And then for the t-test, we did reject the null hypothesis, right? It was 0.049, so it was still less than 0.05. And if you remember, these non-parametric tests, like the rank sum test, they're less affected by outliers, right? So again, because we're not comparing the actual scores, so the actual minutes of moderate activity, we're converting all those scores into ranks, and then we're running a test on the ranks. Whereas the t-test, it's actually running the test on the actual scores or the actual values in minutes. And so it is a lot more susceptible to these outliers, right? Because the t-test is based on a mean, and the mean, again, is affected by an outlier. So if we have this like person with 600 minutes, the mean is going to be, it's going to be drawn to the right or increase, because of that one individual. So that's kind of just a reminder that the mean is affected by outliers, and the t-test again is comparing two means. And so, with outliers or with a skewed distribution or any non-normal distribution, typically the t-test would not be appropriate. Okay, so I'm going to pause there and see if anyone has any questions. And we're done with question 3 now. And yeah, and I will post this program. So you'll be able to basically rerun everything on your own. Okay, awesome. Okay, all right. So question 4 asks, is there an association between age and reported minutes of vigorous intensity exercise? So I'm going to go back and use the data set Okay, let me pause. Okay, so Amanda asked, if we're doing research with this data, would it be appropriate to run several tests on different variables or run one test on all variables like an ANOVA? So it really depends. So what I did actually, okay, so I'm running like this rank sum test, I'm running a t-test, I'm showing you examples with and without the outliers. All of this actually reduces the power of my study. So it's actually very poor practice to be running all these different tests. I'm only running them to show you what the results look like and why it's important to select the correct statistical test for your data and to check the assumptions of those tests before you run that actual test. In terms of running the several tests versus an ANOVA, so an ANOVA would be appropriate if, for example, we were looking at moderate activity by a categorical variable that had more than 2 levels. So, so for example, if we were, and we're actually going to do this today, if we were to look at an outcome by race ethnicity, which in our case was white, non-Hispanic, Black, non-Hispanic, Hispanic, and other. So we have 4 levels there. So that's where we would use, an ANOVA versus say multiple t-tests or multiple rank sum tests. So what we did where I ran basically these like 8 different tests, that's actually not a good habit. This is really for me to kind of show you what it looks like when we run the appropriate statistical test. So in this case, our Wilcoxon rank sum test versus a t-test and how that may or may not differ. In terms of outliers, probably what I would do in the situation like this is if you were, let's say if you were to just run this exercise yourself and you were to remove all of the outliers and give me a justification for why you did that, and let's just say like, well, I looked at them, they meet the rules where, they're over, 1.5 times the interquartile range over the 75th percentile or less than that range, the 25th percentile minus that value. So I ended up removing them from my data set. That would be fine. Or you might argue, I only removed that one extreme outlier because it was definitely implausible. At 600 minutes of moderate activity, but I left everyone else in, and then in that case, you could run the rank sum tests, kind of like how I did. So in that case, you would run just this one where you've removed your outliers, and then you would run this rank sum test where you've left your outliers in. And then you would say, the p-value for both, whether I removed the outliers or included them, the p-value is greater than 0.05. And so I come to the same conclusion that there's no difference in moderate activity by general health status. And that would be okay. You're running just 2 tests. Where it would be inappropriate is if you start running like all these t-tests, maybe I don't know, I'm trying to think of other, if you were to run like all these different statistical tests, a t-test, a rank sum test, and maybe picking out other non-parametric tests, and then, running all of them until you find a test that gives you a significant result, like that's poor practice. So I guess just to kind of summarize, what I've done here is generally not good practice because I know the t-test is not the appropriate test for this data, right? For the moderate activity and for vigorous activity. So just running the rank sum test is appropriate. But in order to see if these outliers are affecting my results, it would be good practice to just run it with the outliers removed and then with the outliers kept in, just to see if there is a difference. If there is a difference, like let's say one is significant and one isn't, then you kind of have to go back and iteratively remove them. Instead of removing them all at one time, maybe you just remove the first extreme value, run your tests, look at the results, I remove the next extreme value. And there are actually programs that will sort of automate that for you. So don't worry too much about, if you do have to do that in the future, you won't have to do that by hand. There would be programs that would automate that for you and then correct the p-value, adjust them for the fact that you're running a lot of statistical tests on your data. So hopefully that helps.
Yes, that helps.
Okay.
So what about like how we're doing it on moderate activity and general health, and then we're doing a separate one for vigorous activity and
So
general health?
so that's okay because you're looking at different outcomes. So that's really okay. It's almost like you can almost view them as two separate, like there's two separate research questions, right? One, you're looking at moderate activity. The other one, you're looking at vigorous health. If you were interested in looking at both moderate activity and vigorous health by general health status, that gets into something that I'm not sure we'll cover. It's more of a multivariate approach because you have more than one outcome. Typically, in most of our studies, we're interested in a single outcome, and then we might have multiple independent variables. So we might be interested in general health, gender, age, race, ethnicity, but that all falls onto the right side of our equation. And those are, still looking at a single outcome. But yes, so the fact that we're looking at moderate activity and then we're looking at vigorous activity, those are really two separate research questions. So it's okay that we're looking at both, and we don't really need to make an adjustment for that. Okay. Okay, yes, yeah, I think you mentioned that too last week, where you're starting to kind of think about your data. If it's the case that you're running, let's say, an ANOVA, right, or like a two-way ANOVA, let's say, then yes, you would have these like post hoc tests, most likely, where you're doing pairwise tests afterwards. But that's a case, for example, for the two-way ANOVA, because you have two independent variables. You still have a single outcome, but you might be looking at time and gender, let's say, for example. And then if your ANOVA is significant, then you're going to want to do these pairwise tests to look at your outcome in time and your outcome in gender. And then that's where all these post hoc tests require some kind of adjustment for the p-value because we're doing all these multiple testing now. So, okay. All right, so hopefully that's helpful. We're going to go back now to where we're looking at two continuous variables. So our vigorous intensity is continuous, and then we're also looking at age. And remember, like age for this particular data set it's like quasi-continuous because they did truncate it at age 80. So anyone over the age of 80 was just set to 80. But we're going to treat it like it's a continuous variable. We're going to use the NHANES Vigorous 1 data. And then, okay, so I asked the question, why are we using this data set and not the entire merge data set? So why not use NHANES, which is just the merge data? Okay, so remember, those have missing observations, right, or values for our vigorous 1 variable. And that might cause issues when we run the analysis. Additionally, even though we recoded them to missing, though, that NHANES, the original merge data set, also includes individuals who simply answered refused or don't know to that question of, how many minutes of vigorous activity do you per day. So we want to remove those individuals who are missing. We can't really we could handle it. And you know what, I'll just stop myself there. There are actually ways to handle those missing values, but for the purposes of this analysis, we're just going to exclude them, which is typically what we would do. In most of our research, we would just exclude them. Okay, so the first thing I'm going to do is look at our age variable. Last week, we already looked at vigorous activity. We know what that looks like. We know we have some outliers. You can even see down here in the right bottom part of my screen, this is the histogram for, I think it's still the one for vigorous activity. It might be for moderate activity. but the vigorous activity looks similar, where it's pretty skewed, and then you have these outliers, at the high end. So I'm gonna copy and paste the histogram and then the density plot code. Okay, you can run just the histogram first. So we're gonna look at age. Okay, and you can see here where I have a histogram of age, and it looks pretty skewed, right? You have it tends to be, looks like most individuals are younger, and then you have, a lesser proportion of individuals who are older. Okay, so we already can see like, it's not really normally distributed. If you go ahead then and load that library, that package, ggpubr, and then run the density plot, you can see pretty similar. So we can think of a density plot as kind of a smoothed histogram. And remember, like, the area under this curve is just equal to 1. And you can see even, from the density plot, the same thing that we see in the histogram, where it's not really a normal distribution. Okay, most individuals kind of fall under the, less than 50. Okay, so some other ways that we can test or look at normality is to run our QQ plot. Sorry, let me just copy and paste these two. All right, so you can go ahead and run just the GGQQ plot. And then you can see here on the bottom right hand of my screen, the QQ plot for age. And you can see that it's at the, at this lower end, it deviates quite a bit, from the normal line, which matches up, right, with our both our histogram and our density plot. Okay, so this is just more evidence that it's not normally distributed. And then the last thing is you can go ahead and run the Shapiro-Wilk test function. So that's this one. Okay, and then remember, our null hypothesis is that the distribution is normal. Our p-value is very small, it's less than 0.05. So we would reject the null hypothesis and conclude that our data, so age, is not normally distributed. And everything we've seen so far, is evidence of that. Okay, so the next thing we're gonna do is do a scatter plot. And from here on out, I think I just use the data that have the outliers kept in. So remember, when we run a scatter plot, we have two continuous variables. We assume that they're linearly related. They should be normally distributed. And in this case, we know that vigorous activity is not. And we also know that age now is not normally distributed. But let's still look to see what the scatter plot looks like. So I'm sorry, we can run a scatter plot, but when we run a correlation, we have to be careful about selecting which correlation to run. Okay, so I'm gonna copy and paste the scatter plot in the chat box for you. And then we can run the scatter plot. Oh, sorry, let me clear that. Okay, and I'm gonna run it again. Okay. So does everyone have a scatter plot that looks like this in their bottom right corner? Okay. It looks really weird, right? So remember when we ran a scatter plot for, I believe it was exercise 1, looking at weight, no, I think it was maybe grip strength and explosiveness. I could be wrong, but I know we looked at a scatter plot for exercise 1 and it looked very different from this, right? This looks like there's there's no relationship between age and vigorous activity. You know, like if I were to ask you to draw a line, you know, that fit the data points best, right? When we talk about this best fit line for our, you know, correlation, I don't think I could draw one. So, and then the other interesting thing that I do want to point out is you can see how like a lot of data points seem to fall. It's almost like at a certain value, right? So I just want to point that out because it kind of makes sense. If you think about if someone were to ask you how many minutes per day of vigorous recreational activity do you do, most people aren't going to report like 22 minutes or 23 minutes. It'll probably be more along the lines of, okay, 30 minutes, 45 minutes, 60 minutes, 80 minutes or 90 minutes maybe, you know, 2 hours, something like that. So even though minutes of vigorous activity is a continuous variable, right? Someone could report 22 minutes and 30 seconds. You know, they could report 22 minutes and 29 seconds, and we can find any like, you know, value in between those two. So it is truly continuous, but in terms of when individuals report their vigorous activity, they're most likely to report it, you know, within these sort of like standard intervals, you know, 15, 30, 45, 60 minutes, 90 minutes, 2 hours, which is why we see these like heavy lines at certain values. So I'm guessing like, for example, this value is probably 30 minutes. So this is 0, 100 minutes. So this value is probably 30 minutes, right? This is probably, you know, 45 maybe, and then this is 60 minutes. And then here, this is probably 90 minutes. Okay, so that's one reason why this scatter plot looks kind of weird. The other thing you notice is that most of the dots, you know, here, they're pretty heavily weighted towards younger ages. So there's 2 reasons for that. Remember when we looked at our histogram and our density plot, most individuals were less than 50 or about that cutoff. And so that's another reason why. So that's the reason why all these dots are kind of clustered more to this bottom left corner. It's just because of the age distribution of our population. Okay, so kind of going back, since you see this scatter plot like this, and we know that age is not normally distributed and vigorous activity is not normally distributed, we actually don't meet the assumptions of the Pearson correlation. So remember, we actually did a Pearson correlation for exercise 1. We talked about it in class. And so remember, the assumption is that they're linearly related and your 2 variables are normally distributed. And that's not the case, right? So for this particular data, in comparison, our Pearson correlation is actually not the best correlation coefficient to pick. So we're actually going to use a non-parametric correlation. We talked about 2 of those. We talked about the Spearman correlation, and we talked about our Spearman's rho, and we also talked about Kendall's tau. So in the first exercise, the Pearson correlation was actually appropriate for our data. In this case, it's not. So again, if you were to actually do a study like this, you would not run this Pearson correlation. You would know, like, that's not appropriate. I'm just going to go ahead and pick either the Spearman rho or the Kendall's tau. Okay, Spearman rho is probably the most commonly used alternative to Pearson's correlation when your data don't meet those assumptions for a Pearson's correlation. But I think Kendall's tau is actually more robust. And what I mean by that is it still performs pretty well when you have a small sample size. In this case, we actually have a very large sample size, right? We have over 1,000 people. It's also less affected by outliers, which we know we have in this vigorous activity data. So if I were to pick between the 2, I probably would pick Kendall's tau. But for completeness, I might also run a Spearman's correlation, just because that's something that you know, the audience for your, for your paper, for example, are going to be much more familiar with. And it's just, it's just used more commonly. So this is a great example of maybe it's not like the best test, but it's the most commonly used test. So if I were to just report the Kendall's tau, people might not be familiar with it. And then they might question, well, why did you use that and not Spearman's correlation? So if you were to run this exercise on your own, you could, pick either of these two. If you were to run a Pearson's correlation, then I would just, let you know, like, I think you may not have met the assumptions for a Pearson. So what alternatives could you have used? And then give these as examples. So you could pick one or the other, or you could do both. Question 4 does ask what amount of variability is explained by age. So what amount of variability in vigorous activity is explained by age? And remember that information is given to us by the coefficient of determination, which in this case, because we just have one outcome variable, one independent variable, we can run a Pearson's correlation and get the R, and then just square that value. That gives us the coefficient of determination. And that will give us the amount of variability in vigorous activity that's explained by age. So in this case, I just ran it so I can show you. So I'm going to copy and paste this. So again, if I were running an actual study and not just this exercise, I would do none of this. And I would just either pick one of these or I would run both. And again, like running one statistical test versus two is not really a big deal. It's really when you start getting into running like lots and lots of pairwise tests, for example, that's when you have to make an adjustment to your p-value. But in this case, I just want to show you, because the question asks what amount of variability is explained by age, we're going to run this just to get the R-square value. Okay. So, our R value is down here. So this is the correlation. It's negative 0.08. It's very close to 0. Which is not surprising, right? Because there really doesn't look like there's any sort of relationship between vigorous activity and age. And then all I'm doing here is I'm taking that estimate. So it's actually, right, so X0 is the R object that I'm creating when I run this correlation test. And then the variable estimate is just the R value in that data set. So I'm just squaring it, right? So the caret and then the 2. And then now I'm printing that value of R squared. So I'm going to run that. And then you can see, just ignore that. That's just the label for that variable, but I've squared it and it's now 0.007. So if I were to convert that to a percent, it's just 0.7%. So very, very little variability in vigorous activity is explained by age. Okay, but let's go back to the main question that's asked in question 4, which is, how are they, so look at the relationship between the two, and we've already determined that a Pearson's correlation is really not appropriate. So I went ahead and wrote out the correlation tests for these two non-parametric alternatives. So let me paste that into the chat. So you should have this code now and you can run it. Okay. So if we look at the result for Spearman, we get the rho value, which is negative 0.1. Okay. We actually have a significant p-value. So even though everything looks like there's really no association, I mean, if the Pearsons came out to very close to 0, and actually the p-value was also significant for the Pearson correlation. The statistical result is that this value is not the same as 0. So there is some positive, there is some, negative association between age and vigorous activity. So in this case, as someone ages, the amount of vigorous activity decreases because this is a negative value. And that's actually statistically significant. So if you were to answer question 4, you could report this. You could report Spearman's rank correlation rho, and you could just say, there's there is a statistical like association between the two. As someone ages, the amount of vigorous activity decreases. So that's how you would respond to question 4. We could also run Kendall's tau, and remember that's a little bit more robust. So it's, if you have a small sample size or you have outliers, then Kendall's tau is a little bit more powerful than Spearman's correlation. And then if we look at the result for that, it's actually pretty similar. So the tau value is negative 0.08, and it's significant. So again, what you could just say is that there is a significant association between age and vigorous activity. As an individual ages, the amount of vigorous activity decreases. So the interpretation, whether you use actually, even if we use Pearson's correlation, the interpretation is the same for all three of these tests. But for our data, these two would be the more appropriate tests to use. Okay, I'm gonna take give a 5-minute break if you guys want to ask questions, because we're gonna go into the diagnostics for linear regression, which can get a little bit heavy. So let's just pause there and see how everyone's doing. And once we do that, it should be, I think question 5 wasn't too bad, if I remember correctly. Okay. Okay, awesome. I always worry when I'm doing this that I'm just exhausting everybody because I know it's a lot. It's definitely a lot because you're, yeah, I totally, right, exactly. That, yeah. Because you're not only learning how to code, you're also trying to apply a lot of these concepts that, right, we only, for example, for the correlation, I think we just, we had one lecture and then one review, so it's hard because there's, not only are we learning all of these different tests, we're learning that there are these non-parametric alternatives to these tests. And again, we're ahead in lecture for some things, but we actually haven't had a formal lecture for these non-parametric tests. We talked about them in lecture, right? If you don't meet these assumptions, here are alternatives, but we haven't had a single lecture where we talk about non-parametric tests. So I know it's a lot. And even with just ANOVA, it's so many different versions of ANOVA. And so, picking out when to use what can be really overwhelming. So again, that's where I think having a flow chart will be really helpful for you guys. But yeah, so yeah, part of me just feels bad because I know it's a lot. It's concepts, applying those concepts and learning how to code all at the same time, which is definitely a lot. So, but you will have this program, and I tried in all of my comments to be very explicit about what I'm doing and why I'm doing it. So hopefully, when you go through exercise 2 on your own, maybe it'll make a little bit more sense. If you have, obviously always, if you have questions, you can always, email me or come to office hours too. So, okay. So let's see. Is everybody is everyone ready? Do you feel ready to keep moving? Okay, awesome. Okay, so we're going to start here. So remember, this is for just demonstration. I would not expect you to do this in the exercise. But what I wanted to show you was, when we run like a linear regression, what are some diagnostics that we can, what are some things we can do after we run that regression to check the assumptions of the linear regression? So we already know, given the distribution of age and vigorous activity, that Pearson's correlation is not appropriate. Those two variables are, they're not normally distributed. And if you remember from like many weeks ago, we talked about how a simple linear regression where we have a continuous outcome and a continuous predictor, and that's it, no other variables, it's actually equivalent to a Pearson's correlation. So we can actually run a linear model on age and vigorous activity, where age is our predictor or X variable, and vigorous activity is our outcome or Y variable. And then look at the results of that, and then run diagnostics to see, where our assumptions met for, and so if you remember, the assumptions for a linear regression is that there's linearity of the data. So the relationship between X and Y is linear. There's normality of the residuals. So remember, the residuals are it's the difference between the actual data point value and the fitted line or predicted value. Those are our residuals. We assume that the errors, so those residual errors are also normally distributed. Then there's this concept of homogeneity of the variance of the residuals. So that's the homoscedasticity, right, where the variance is consistent. And then that there's independence of the residual error terms. And so those are the 4 assumptions for our linear regression. And then we can go ahead and run our linear regression and then use this like nice, it's actually in the this package, GG Fortify. So we'll load it, we'll install it and load it, and then run these diagnostics. So I'm going to copy and paste the linear regression code. Okay. So what I'm doing here is I'm using this linear model function LM. I'm creating an object called my linear model, and then I'm going to run a summary on that to look at the results of the linear model regression. N Haynes vigorous activity is our Y variable, and then this tilde it's kind of like our equal sign, and then everything to the right of that are our predictors and our covariates, our X variables. So in this case, age is our predictor, so that's our predictor variable. Okay, so I'm going to go ahead and run that. When we get the summary of the linear model regression results, this is what it looks like down here. Okay, so you might, I think most of you in your projects will probably run some variation of an ANOVA, but I want to show this in case you do end up doing any sort of regression models. And we will later in lecture talk about categorical models as well. So for example, because our outcome vigorous activity is continuous, we use linear regression, but there are instances where you might be interested in an outcome that's binary. So your outcome might be a simple yes, no. Did they, have a disease, for example? And we would use a different type of model for that. So we'll talk about that later in the course as well, just in case you end up using, these multiple regression models. But this is what the output looks like. These are our estimates, our beta estimates. This is the standard error of those estimates. And then this is our p-value. Okay, and then this is our t-statistic, our test statistic. But it is the t-value in this case because we're running a linear regression. So we're actually looking at means, just like we are for our t-test. So this variable is our primary predictor, or actually in this case, our only predictor, right, age, and we have this estimate of negative 0.29. So what does that mean? That corresponds to our beta when we had the equation in the slide and we had y equals beta naught plus beta 1 x1. So that just corresponds to our beta 1. And x1 in this case is our age. Remember that beta naught is the intercept, so this is beta naught. Okay, and so that's where it crosses the y-axis. Okay, but let's look at beta 1, the coefficient for age, that's negative 0.29. So what that means is for every 1 unit increase in age, or in this case, so it's a year, so every 1 year increase in age, there's a there's a 0.29 decrease in number of minutes of vigorous activity. So this is great, right? Because it's consistent with all of the findings that we found with the 3 different correlation tests that we ran, where the values were all negative, meaning as someone ages, the amount of vigorous activity decreases. The nice thing here is we can quantify it when we run our linear model, where every 1 year increase in age, on average, there's a 0.29 minute decrease in number of minutes of vigorous activity per day. And this finding is statistically significant. So our p-value here for that beta 1, our beta 1 coefficient is less than 0.05. So we would say that this is a significant association. And in this case, because it's negative, it's a significant inverse association. Okay, so we ran this linear model, but we don't know if the data have met the assumptions of our linear model. So I'm going to copy and paste the code that we can use to run these diagnostics. So the first thing is going to be to install and load this package called ggfortify. And if you look down here in the console, it must be like an older version. I don't know. Maybe there's like a newer package that does this as well, but it still runs. So if you go ahead then and run, so this is just parsing out the window. So you can see here, right? Typically when we run a figure, we just have that single figure. This is just saying, create a 2x2 plot. So hence we have these 4 panels here. Okay, this first panel is looking at that first assumption. If there is linearity, if there's a linear relationship between our 2 variables. We do have a horizontal line. And so that does actually kind of, it's very small, I know. It might actually not be completely horizontal if we were to blow that up a little bit. If it was just, completely straight and horizontal, then that would indicate that there is a linear relationship. Okay. This is our QQ plot. So remember, we can look at the QQ plot when we're looking at whether a variable, like moderate activity or vigorous activity is normally distributed. This is just a QQ plot for the residuals, because the assumption is that one of the assumptions for our linear model is that the residuals are normally distributed. And in this case, you can see that they're not. And these are identifying sort of like extreme values. But here's our normal line. So I'm just in the bottom right corner of my of our studio right now, and you can see that the residuals really deviate from that normal line. So we can just kind of come to the conclusion that we don't meet that second assumption, for a linear model. And I think if I were to blow this up, we probably don't meet the first assumption either. Okay. This third panel is looking at homoscedasticity, so whether there is sort of consistent variation in the residuals, so the homogeneity of variance. And And if we were to have a horizontal line, and again, I'm sorry because it's very small, but it's not truly horizontal. And we had equal spread about that line, which that's definitely not the case, right? You can see like it's a little bit more spread out here and then more clustered down here. If it was truly homogeneous in the variation, it would be all, maybe clustered equally around this line, but it's not. You can kind of see like down here, the points spread out a bit more, and then they kind of spread out more up here. So I don't think we meet the third assumption either. And then the last diagnostic is, oh, okay. I'll pause there until, okay, so you guys are getting an error for this one, for the plot. Okay, so what I'm gonna have you do is, you see this broom right here? Oh, interesting. What? Okay. And that's interesting because we did not use a $ in any of this code. Okay, so one thing I will have you do is maybe click on this broom. And then see if, so for those of you getting an error, were you able to load GG Fortify? Okay.
Yeah, it looked like the GG Fortify loaded. I only got two of those graphs. I just got the top two.
Oh, okay. That's interesting. So click on this broom and this will just clear in case there's background code in some of these other functions that we've used where it's just, so remember like I plotted something and it ended up just in this corner right here. So that 2x2 parsing of the figure was like still there in the background. So click on that broom and just see if this works. It might not. Clear all plots. And then go ahead and rerun these two lines where you're parsing out that window and then plot your diagnostics and just see if that works. Did that help? Okay.
I still got just the two.
The two. Okay.
Two, yeah.
Okay, that's really odd. Well, the good news is I don't expect you to do this for the exercise, so you don't have to do it. But the bad news is, obviously, if you were to run a linear regression later and you wanted to run these diagnostics like this, then this code isn't helpful to you, right? Let's see, let me look at the time. If you don't mind, what I'm going to do is just finish talking about this last figure here in the bottom right corner. And then I want to finish exercise 2 today. And then what we can do is go back. And again, because not being able to run this or only getting these two figures isn't going to restrict you from being able to complete the exercise. So I'm just going to finish the exercise. And then after class, and I will probably finish a little early if you want to stay and like share your screen and we can kind of figure out maybe what's going on. So anybody who's having the error can just stay and we can troubleshoot it and see why. And it might be because this package was created like, it looks like under a different version of R. So that might be part of the issue, especially for you guys, if you just installed R at the start of the semester, you're going to have a much newer version. So, okay. All right, I appreciate it. Okay, I'm just going to quickly talk about this and then we'll go through question 5 and then I'll stay behind so that we can kind of look at why you're only getting this top 2 figures here. Okay, so for this fourth panel, it's looking at residuals versus leverage, and it's used to identify influential cases. So these are just like extreme values. And remember, we do have outliers, like the data set that we're using for vigorous activity, we still have outliers in those data. And, and that can actually affect our results. So this is identifying, and I know again, it's very small, but it is identifying observations here. So like this person, observation 82, that potentially has a value that is heavily influencing our regression results. So it might be where we would then go back and identify that individual and remove them from the analysis and rerun the regression. So again, this is another instance where you would run your analysis and then iteratively remove the outliers rather than removing them all at one time. Or if you were to leave them all in and there didn't appear to be any observations, even if they are truly outliers that are influencing your results too heavily, then you would probably choose to leave them in. And again, because those individuals might have data, variables other variables that you might be interested in. And if you remove them, you can no longer include them in any of your analyses. So you wouldn't be able to look at any of those other variables. You've kind of lost them essentially at that point. Okay, so that was just kind of a quick look at linear regression, how that relates to Pearson's correlation, and then running these diagnostic tests for your linear regression. And it just looks like, based on all of these results, that we don't meet the assumptions for the linear regression, which we expected, right? And which is also why we decided that a Pearson's correlation is not the appropriate analysis for these particular variables. Okay, this is redundant because we already looked at R squared. So I'm just going to delete that actually because we did that up here. Okay. All right, so these are the diagnostics. Okay, so now we're on question 5. Question 5 asks if there is a difference in reporting of minutes of sedentary activity by race and ethnicity. And remember, our levels for that, or our categories for that, is white, Black, Hispanic, and other. Okay, the first thing we need to do is look up sedentary activity, because so far we have not used this variable in any of our analyses. So we need to actually find out what the variable name for that is. So I'm going to share my screen, change it over. And remember, we can go to the NHANES data set. Let me just go back. Okay. And go to the questionnaire data. Okay, so I was already there. And then go to physical activity. Okay, and then the documentation for that. So here, actually, it's right here, is minutes of minutes of sedentary activity. So the variable name for that is PAD 680. And then remember, they have these frequency tables, which is really nice. So we know the range of values is 0 to 1,380, which already looking at that is probably not really plausible, right? If I were to, let me just do that actually, 1380 divided by 60, it's 23 hours. So that might be somebody, maybe it's somebody who's bedridden. And so they are sedentary, for that, number of hours. But actually, when we look at the description, it's more like sitting, watching TV, traveling, so commuting, and it doesn't include time spent sleeping. So 23 hours is probably not feasible, right? Because that would then mean that this person is only sleeping for an hour a day, and then the rest of the time they're engaged in this sedentary activity. So probably an incorrect value. And then here we see that in our total sample of 9,000 people, So that includes individuals who are younger than 20, because remember, we remove them for our particular analysis. That we do have individuals who refused to answer the question or they just didn't know. And then we have about 2,000 individuals who are missing. Okay, so that gives us a quick idea of what that variable looks like in the overall data set. So I'm going to go back to RStudio now and then just go back to the question. So here we have a continuous outcome variable, right? Sedentary activity. And we're interested in looking at whether there's a difference by this categorical variable that has more than 2 levels. So what in this case would be the appropriate statistical test if our assumptions hold for that test? But what's kind of the first thing that pops into your head? So when we're looking at a continuous outcome and by a variable that has 2 levels, we're running a t-test. If we have a categorical variable or factor with more than 2 levels, that's when we would run an ANOVA. So, and that's just a straight one-way ANOVA, and that is an instance where we're comparing means for a single outcome variable for a factor or a categorical variable that has 3 or more levels. But there are some assumptions for that test, right, for the ANOVA. But that's the first thing that would come to mind. So, okay, so that's the answer to that question. If the assumptions hold, then we would run an ANOVA. So first thing, let's set up the sedentary activity variable. So I'm first going to look at what it looks like in our data. So remember, we have about 5,000 individuals in our Ann Haynes data, right? Because we restricted to individuals who are older than 20. In this case, we have a range of 0 to 9,999, and we have 11 missings. So remember, those 9999s are people who just didn't know, and the 7777 are people who refused. So we're going to want to remove those individuals or set them to missing at least at first, right? So just like we did with the moderate activity and vigorous activity. So I'm going to copy and paste all of the code here and send that to you in the chat so you can run this as well. So remember, whenever we're modifying a variable, it's good practice to rename them. So I'm creating this new variable called sedative activity. And it's just the same value as the original variable, which is PAD 680. So I'm going to run that. Okay. And then the next step is to set those values of 777, 7 and 9999 to missing, right? If we were to include them in an analysis, like they would definitely be outliers. They go way beyond 24 hours. So we would not want to include those in our analysis, okay? So we're going to remove them or set them to missing. And then now what we're going to do is create this new data set called N Haynes underscore sedative 1, or not sedative, sedentary 1. And that is a data set that is analogous to our moderate one and our vigorous one, where it's everybody with a non-missing sedentary activity value. So we're just removing all of the missings in this line. Okay. So now that we have this new sedentary activity variable that has all of the missings removed, actually, let me go to this right-hand window. You can see here that there weren't a whole lot of people that were removed, which makes sense, right? We just had 11 people missing here, and there weren't too many individuals with a don't know or refused value when we looked at the frequency table on the N Haynes website. So it's kind of nice, like we didn't really lose a whole bunch of people. So now let's look at how sedentary activity is distributed. So right, for the ANOVA, we would want our outcome variable, so in this case, sedentary activity, to be normally distributed. So let's see what that actually looks like. So I'm gonna clear my window. So go ahead, and if you have those figures still in your window, hit the broom and clear it. And that's gonna clear also that parsing of the window to a 2x2 figure. So I'm going to run, sorry, let me copy and paste this for you. Okay. And then, okay. So if we look at the histogram, it looks pretty skewed. Or actually not super skewed, but it looks like we do have some outliers, which we know we probably do, based on the minimum and not the maximum here, but even like the third quartile is 8 hours. But that might be someone with like a desk job. So that actually does seem feasible. But you can see someone out here like at 1400, which is quite high, right? And there was actually someone in the full data set that had a value of 1380, which again is 23 hours, and that's probably an error. Okay. So let's just other looks at the data to see if it's normal. So the QQ plot, we could run that. And actually, if we look at it, it doesn't look too different from normal. It kind of does maybe down here, and maybe even a little up here, but it's not horrible. And then I actually did try to run this. I don't think it'll work. The Shapiro-Wilk test, right. Okay, our sample size is actually too large to run this. So far I'm gonna say like, maybe it's normally distributed if we remove those outliers, right? So let's just, here's another look to see what our data, how it's distributed. I think we already loaded this package car at the very start of class, but let me go ahead and copy and paste that so you can run it yourself. So I'm gonna go ahead and run that. Okay. So it does look like, maybe our data is just like a little bit skewed, but not really. I think more of the issue of why it doesn't look totally normal is that we have these outliers here. Okay. R gives us the observation numbers for those top 10 extreme values. So this code here, again, just like we did for moderate activity and vigorous activity, is just identifying the values for those elements or observations in the data set. Okay, so I copied and pasted that there, and then I'm just gonna go ahead and run that code. And you can see here, like the most extreme value is 1380, which is 23 hours. So that's probably not really feasible. 1080 corresponds to 8 hours. Again, that might be somebody who's sleeping 6 hours a day. They roll out of bed and maybe commute right to work and then have like a desk job. But it still seems like quite a bit of sedentary activity, right? Especially because it doesn't include sleep. So maybe it is an outlier. Okay, and then I'm just gonna go ahead and copy and paste the next chunk of code. All right, so the next thing we're gonna do is look at our box plot stats. That's just going to identify all of the individuals who are considered outliers according to Tukey's rule, and give the values for those outliers. And it looks like the lowest is 900 minutes. And that corresponds to 15 hours. Okay, so that's somebody who maybe is sleeping for 8 hours or maybe less, and then has some, activity, and then the rest of the time they are completely sedentary. Which, maybe that is feasible. that's a lot of sitting and doing nothing, but it could, it might be feasible, especially for someone who maybe has a long commute and then goes directly to a desk job, sits through lunch, for example. So it is possible, but according to Tukey's rule, it is still considered an outlier. Okay, we're going to do the same thing that we did for moderate activity and vigorous activity, and I'm going to keep the naming convention the same. So remember, we did all these, like for moderate activity and vigorous activity, we sort of removed the most extreme outlier, and then we looked at the histogram again. Then we removed more outliers and looked at the histogram again. So we had this, _1, 2, 3. Here, I'm just going to go straight to NHANES sedative 4. So this is basically creating another data set that's exactly like the NHANES sedative 1, where I have non-missing sedative activity values. Not sedentary activity values. That way, if I do decide to remove the outliers, I have this new data set where I've removed them. So you should have that code. So go ahead and run that. And then here is the code to identify the outliers and then decide whether we want to exclude them. Okay. When we look at the results here, there were 95 outliers out of like 5,500 individuals. Okay, so that comprises of 1.7%, which is actually a really, really small percentage. It's a pretty small percentage. The mean of the outliers is quite high, so it's 968 minutes. So that's like 16 hours. The mean without moving the outliers versus if we keep them in, they're actually pretty similar. For me personally, because it's such a small proportion of individuals who are considered outliers in these data, and because the mean of the outliers is so high, and then if we look here, it probably is the case, that these are outliers, and without them, it looks like sedentary activity is like somewhat normally distributed, but really because it's such a small percentage of individuals that are considered outliers in the sedentary activity, I'm going to go ahead and remove them. So if you remember, for moderate activity, it was closer to something like 17%. And for vigorous activity, I think it was like 5%, which is still pretty small. In the case of moderate activity, I might do kind of what I talked about, where it's like I iteratively remove them, and then you maybe use this like an automated program to do that, as well as run my analysis and then do these diagnostic tests where I'm looking at whether those outliers really influenced my results. And if not, then I would just leave them in. Even though I know that they're outliers, if they're not, really influencing my results too much, then I would just leave them in so I have more complete data. In this case, it's such a small proportion, so I'm just going to go ahead and remove them. So I'm going to put yes, and you guys can go ahead and put yes as well. And remember, it sets those 95 outliers to missing, so we're going to want to remove them. And I'm creating a new data set, sedative 5, with the outliers removed. And that's analogous to our moderate 5 and our vigorous 5 data sets, where the outliers are completely removed. Okay. Looking at the histogram for sedentary activity with the outliers removed, it looks normal enough to me. And if you look at the box plot, I know it's really small, but that also looks like normal enough to me. You might go ahead and run like a test to look at skewness. You might also look at kurtosis before you decide whether or not you want to run an ANOVA. But based on these results, I would say, I think we can go ahead and proceed and run an ANOVA. So let's go ahead and do that. Oh, here, okay. All right, so what I've done here is I am just running the histogram again and a QQ plot. So I'll paste that in here so that you can look. We still have more than 5,000 people, so we wouldn't be able to run a Shapiro-Wilk test. There's probably a function to run that test maybe on a larger sample size. If I find one, I'll send it to you guys, but Okay, so this is the same histogram, it's just bigger. It's interesting that there's this gap here. Oh yeah. Sorry about that. Okay, so yeah, so it would be just this last line here. Okay, and then I'm gonna run the QQ plot as well. It looks like it probably is not, it's not perfectly normal, right? We have like some deviation here. Okay, is everyone good? Do you have your sedative 5 data set? Okay, so now we can actually run our ANOVA. So I'm creating this new R object called res.aov. This is the function to run the ANOVA. The outcome variable is sedative activity. The predictor is race. So remember we created this race variable in a couple weeks ago. It's white, black, Hispanic, and other. And then our data set that we're drawing from is this data set with the outliers removed. Okay, so I'm gonna run that. It's not gonna give me a result. I have to do the summary of that analysis. Let me copy and paste that for you too. Okay. Okay, so if you look down here, our p-value for new race is less than 0.05. It's actually very small. It's 2 to the negative 16th. So remember, our null hypothesis for the ANOVA is that all of the means are the same across all levels of our categorical or predictor variable, in this case, race. So the means, population means for each of those groups, white, black, Hispanic, and other, are the same. Our p-value is less than 0.05, so we reject that null hypothesis and conclude that at least one group is different. So remember, the ANOVA test is, or the F test is an omnibus test, right? It's just like overall, they're all the same, and then the alternative is like there is a difference, but we don't know which one is different. So what we have to do then, when we get a significant ANOVA, is to then run these post hoc tests. So we would run pairwise tests looking at, for example, white versus black, white versus Hispanic, white versus other, and then all of the other possible pairs between those groups. And because we're running multiple tests, we also have to adjust for the fact that we are running all of these multiple pairwise tests. Okay. So here, so since the ANOVA was significant, one thing that we can do is we can run the Tukey honest significant differences. So it will perform multiple pairwise tests and then have some adjustments. So I'm going to copy and paste this. So this is just one option. So I'm running that on my output, res.aov. Okay, and then this just gives us the result. So black versus white. This is the difference in means in sedentary activity. So if you were to subtract it, the mean for our black non-Hispanic group is 32 minutes less than the mean for our white non-Hispanic group. These are the upper and lower bounds for that estimate, and then, or I'm sorry, for that difference. And then this is our p-value corresponding to the difference. So for this pairwise comparison, black versus white, there is a statistically significant difference between those two groups. So that's one pair that's different. And then Hispanic white is another pair that's different. If we look at other white versus white and other versus black, those p-values are not statistically significant. So those are both greater than 0.05. So using this method, there is no difference between white and other, and no difference between black and other. But there are differences between the other pairs. And this p-value is adjusted for the fact that we have these 6 comparisons. So that's one thing that we can do post hoc. We can also do pairwise t-tests. And I think that's probably more common. And then it has this option of adjusting the p-value and specifying what method we want to use to adjust the p-value for the fact that we have these multiple tests. And in this case, I'm selecting BH, which stands for Benjamini and Hochberg. But I'm going to copy and paste this code, and we can look actually at this p-adjust methods to see what our options are. So if I were to run this, so this is the argument p.adjust.methods, and I'm just putting a question mark there. So that's going to actually give me some information in the bottom right-hand corner here. So if you look in the bottom right-hand corner of your RStudio screen, you can see that these are the different methods, or sorry, these are the different options for that p.adjust.methods argument. And then down here, it describes to you what those options correspond to. So for example, Bonferroni corresponds to the Bonferroni correction. Okay, and you can actually do that with, I think, any function or any argument. You can put a question mark in front of it, and it'll give you the documentation for that. So let's go ahead and actually run the pairwise tests. Okay. And if you look down here, yeah, it is super cool. It's kind of nice too, because you don't have to, remember, you can run like these individual t-tests, and then you'd have to go back and like adjust for them somehow. So this function is really nice because it does that for you. So this is basically just a matrix of our different, possible groups. So we have black versus white. So this is blanked out, right? Because it's just black versus black is the same group. The black versus non-Hispanic, or sorry, Hispanic is blanked out because that pair comparison is actually here where we have Hispanic and black. So this is just all the possible pairwise comparisons. There are 6. And then it's just giving the p-values for those different comparisons. Okay. So again, like the result's actually a little bit different than the Benjamini-Hochberg, than the Tukey on a significant difference, where up here we had no difference between other and white and other and black. But if we look at other and white, we actually get a significant p-value here, and that's adjusted using this method. This is consistent, where black and other is not significant, and then everything else is statistically significant. This is probably one of the more common corrections or post hoc tests and corrections is running t-tests, post hoc t-tests after you get a significant ANOVA result, and then using this adjustment method. So it's okay that the results are a little bit different, right? Where other versus white is different using this method versus this adjustment method. That's where you just have to be very clear about what method you use. So when you write this up, you would say, ideally decide beforehand. So even though these are post hoc tests, it's best practice to decide what post hoc test you're going to conduct before you actually run your analyses. So in this case, let's say I already ahead of time, I'm going to run the ANOVA. If the assumptions are met, if my data meet the assumptions of that test, and then state in my method section that if I have a significant result, I will run post hoc pairwise t-tests with an adjustment, p-value adjustment using the Benjamini and Hochberg method. So I would specify that and just be very explicit, and then in the results, I would share these. Okay. So for question 4, I believe it also asks us to look at moderate activity and vigorous activity, which we already know is not normally distributed. So in this case, an ANOVA is not appropriate. So we don't really have time to run this before 11, but I put this code here. So the Kruskal-Wallis test, which again, we just kind of like threw into a lecture slide as an alternative to the non-parametric alternative to the ANOVA, can be used when we are comparing. So we have a continuous outcome, and then we have a categorical predictor with 3 or more levels. So it's really just the non-parametric alternative to an ANOVA. And I've included the code here, and using sedentary activity without the outliers removed. Because remember, when the outliers were still in the data, they looked a little bit skewed. Also, outliers affect the mean, whereas they're not affected by these non-parametric, they're not as affected. These non-parametric tests are not as affected by outliers. So what I've done here is I've basically just run a Kruskal-Wallis test for the sedentary activity outcome variable with the outliers included in it. And you can go ahead and do that for moderate activity and for vigorous activity, whether or not you decide to exclude those outliers. Okay, so the results actually look the same. Actually, let me just run this really quick. I'll post this program as well, so you guys will have this code. Okay, so I'm just gonna just run this to show you what it looks like. Oh, sorry, let me run the test first. Okay, so I'm running the Kruskal-Wallis test. This is a non-parametric alternative to the ANOVA. Don't worry about running it. I get a very small p-value, so I reject the null hypothesis that the sedentary activity is distributed, has the same distribution. So remember, we're not talking about a normal distribution or means. We're just talking about the distribution kind of more generically. So the distributions are the same across all race ethnic groups. We reject that null hypothesis. So at least one group is different. So one group has a different distribution. And then this done test is just one way of looking at which group is different. So I ran that function, the done test, and then now I'm just going to show you what it looks like. Let's see. Okay, so these are the pairwise comparisons. So this would be kind of like analogous to our, pairwise t-test, for example. So we're looking at Black versus Hispanic, and so on. It gives you an unadjusted p-value and then an adjusted p-value, and all of these are quite small. So it's actually the interpretation of this result would be that all of the pairs are different. Okay, and then the last thing I want to show you is just another option for a post hoc test if you get a significant Kruskal-Wallis test result. Okay. So the done test, I just want to note, and I have it in my comments, is that it can be used when you have unequal groups. So different number of observations in each group. And actually, okay, so this didn't run, which actually makes sense. I just put this code in here for you to look at. Let me write this. No one can be used. Okay. Oh, I had it here. Okay. We can only use this post hoc test if we have an equal group. So equal number of observations in each group, which we don't have. We don't have the same number of people in the white group, Black group, Hispanic group, and other group. So we actually can't, this test is not appropriate. So in that case, the done test is the more appropriate post hoc pairwise comparisons. So I put this code in here so that you can go ahead and use the Kruskal-Wallis test and the done test for your post hoc testing for moderate activity and vigorous activity. And then again, your predictor variable is still going to be new race. So it would basically be all of this code, and you're just going to change the data set and the variable name. So go ahead and try that. I would say like give yourself maybe, you know, like a week to complete it. So maybe try to turn this in by next Tuesday. But I'm also very flexible. So if you're having issues, please reach out to me if you are having issues so that I can help you. Or if you need to turn it in later, that's okay too. But go ahead and try the moderate activity and vigorous activity by race on your own. And that's just like the second part of question 5. So that's all I had for today. I will post this R code onto Cougar Courses. And then for those of you who had an error when we were running that diagnostics plot, if you want to stay behind, I have a few more minutes. So I'm happy to stay and then kind of see if we can figure out what was going wrong there. Let me save this program to you before okay.
Thank you.
Thank you very much. I appreciate you coming today.
Thank you.
Thanks,
I'll
everyone.
I'll be in office hours this Friday.
Okay, thank you very much. I look forward to it, Sebastian.
I'll see you later. Have a good day.
Bye, you too. Okay, so for those of you still on, if you, let me allow you, so Alex, I'm gonna let you share your screen. I'm gonna make you a co-host. So if you wanna go ahead and share your screen. Okay, and then, yeah, so we're gonna scroll up a little bit more, I think, to where the, okay, interesting. Okay.
It was one, right? The GG Fortify one.
Uh-huh.
Okay, yeah, because I only got 2 graphs myself.
Okay, can you highlight, like install, like highlight 483 and 484 and just run those lines anyway, and just so I can see your output. Okay.
More package.
Oh, are currently loaded. Okay, wait.
So should I just
R project all install. Are still can restart R before installing the requested packages all again. Oh, okay. Click yes.
Okay.
So it will save your workspace.
Cool.
Yeah, because like going back and like creating these data sets again are yeah, not fun. Okay, so it looks like you have everything. Awesome. Okay, now try to rerun 483 and 484. Oh, that's weird. Now your environment's empty. What?
Oh gosh.
Okay.
Well, that's gonna suck if that's gone.
Yeah, I know, right? Okay. Let's just see. Okay. Oh my God.
Mine, after I did, like, I reinstalled and restarted R. So.
And it still didn't work?
No, mine did work.
Oh, it did work. Okay.
You just have to restart it.
Okay. Okay, so April, you're good then.
Yeah. Well,
Okay.
thank you.
Okay, awesome. All right, I'll talk to you soon.
All right.
Okay.
Bye.
Bye. And then Alex, go ahead and highlight 485 and 486 and see if that works. It might not because we lost all of our objects.
Yeah, probably.
Yeah. Okay, here's what I'm going to do. I am going to, hold on one second. Okay, I'm going to go into my R. I'm going to send you that object. Wait, I don't know if I can actually. Okay, hold on one second. It is based on vigorous activity 1. Okay, hold on one second. I'm going to send you code that you need to create the data sets that you need so that you don't have to like scroll up and find them. So, okay, so I'm going to go into chat. Okay. Oh, okay. All right, go ahead and run that code. Then, all right, now, and then I will send the rest of the code that you need to run. Get that.
Oh,
Okay.
what? Tell me to restart my RStudio.
Again. Oh, okay. It was not able to autosave this file. That's okay. I would just say okay.
Okay. So, I mean, let's see.
Oh, because you don't have the NHANES data either.
Yeah.
Okay.
Yeah, it's
You, okay, okay. I will send you the NHANES data. Hold on one second. Okay. If you download this data set and then import it.
Okay.
Yeah.
Okay, let's go back. Import. Okay, now where did I put that? My documents, it is. Okay. Okay. All right.
Okay. Oh man. Okay. View NHANES 3. Oh, is that what you? Okay, okay.
Should I just go back and download all the like individual files?
Yeah. So okay, go to import data set. Oh no, actually, did you ever save your NHANES data? Like the merge data set?
I had the stuff that was the original NHANES that we started off with this exercise with, and then I had, I think, the mod 1, I think, saved.
Oh, okay.
So
You
that's
should be able to, or were you able to click on this file in the chat, the click to open this
Yeah.
okay, and save it to, so cancel out of this.
like just erase it.
Yeah, that's fine. Go to the NHANES, so click on this NHANES.r data in the chat and save that to, I don't know, wherever your C drive.
Okay. Where'd my little cursor go? There it is. Okay. Okay. So it's right there.
Okay. I'm wondering if you can import it now.
That's fine. Importing it to R, but let's see if it's gonna do anything.
Oh shoot, I'm gonna stop recording too.